Welcome guys now to this video, which is a very detailed video on proving the laws of indices. I'm one of those people who believe anything you do in mathematics, it's always good to give a proof, and therefore welcome to this video guys. It's very important because it shows you how we came up with the laws of indices. Of course, there's this general statement about what these videos I'm producing are all about. All right. All students or those students doing mathematics as a compulsory subject, or maybe they have done mathematics but they have forgotten, this video is suitable for them. More so, when watching this video, please have a pencil and a paper ready to work through the questions before reading their solutions. Or before reading the solutions, because the video contains the questions and the solutions. And before you tackle any question, please read carefully before you attempt it. All right? And it is very important that you try hard to complete the question on your own. Don't refer to the solutions when you get stuck. If you have yeah? In the middle. For that interruption, I don't know. The camera has just gone off, but I was saying, you read the question completely on your own and you don't look at the solutions when you get stuck. If you have read the problems, you can just go back to the textbook. And that way now you can look at the answers after that, but not before that, guys. Proof of the laws of indices. The laws of indices are also known as the laws of exponents. And there are rules that describe how to manipulate mathematical expressions involving powers of the same base. These laws are fundamental in algebra and are as follows. Algebra to any level you want, and they are as follows. So you have the laws of indices. Of course, we had mentioned them when we were looking at the topic indices area. So we very simply we go over them. We have the power of powers rule, the product of powers rule, sorry. Then we have quotient of powers rule, power of a power rule, power of a quotient rule, power of a product rule, zero exponent rule, and negative exponent rule. All right. So let's start with our first law to prove product of powers rule. So that is the law a raised to m times a raised to n equals to a raised to m plus n. So to prove, we do the following. Just consider a general case of a raised to m. So the meaning of a raised to m means a times a times a times a m times. And a raised to n means a times a times a times a n times. When you multiply a raised to m by a raised to n, we are effectively multiplying a by itself m times and then n times. Do you believe that, guys? All right? So, let's take I've got 2 squared times 2 squared. 2 squared means that I'm repeating 2 times. And the other 2 squared means I'm repeating 2 squared. So, it's like I'm multiplying 2 squared times 2 squared. All right? And when you look at 8, you have 2 times 2 times 2 times 2. And you get the 2 times in the first 2 and the 2 times in the second 2. When you add them, they become 4. So it will just be like now 2 raised to 4, which is 2 times 2 times 2 times 2. So, in a similar manner, a raised to m times a raised to n is equal to a times a times a times a m times a times a times a times a n times. This is equivalent to multiplying a by itself m plus n times. Okay? Like this 2 squared times 2 squared is like multiplying 2 by itself 2 plus 2 times, which is 4 times. So m times a raised to n is equal to a times a plus times a m plus n times, which is equal to m plus n times. Quite easily done. Quotient of powers rule. A over m raised to a over n equals a raised to m minus n. So you assume, here you have to assume before you prove that m is greater than n. Because if m is equal to or less than n, there will be issues. So we assume m is greater than n. Therefore, we can now write am and an as the way we had written before in the product rule. And when you divide now a raised to m by a raised to n, all right, the n factors of a in the numerator and the denominator cancel out. Leaving m minus n factors of a in the numerator. All right. Remember, m is greater than n. And therefore, a times a up to times a, m minus n times equals a raised to m minus n. Power of powers rule. A raised to m, everything again raised to m is equal to a m times n. A raised to m times n. And the proof is that if you consider a raised to m, that's what you get. The same as a times a times a times a m times. Now raise m, a raised to m to the power n. And you find that it is a raised to m times a raised to m times a raised to m n times. Each a raised to m is multiplying by itself m times. So we are multiplying a by itself m times n times. And therefore, a raised to m raised to n is equal to a times a times a times a m n times, which is the same as a raised to m n. Power of product rule, ab raised to m is equal to a raised to m times b raised to m. Proof, consider ab raised to m, and you find that it is ab times ab times ab m times. By the associative property of multiplication, we can rearrange the terms, where we have now ab is to m is equal to a times a times a, m times b times b times b, m times, and the answer becomes a raised to m times b raised to m. Power of a quotient rule, proof, a over b raised to m is a raised to m over b raised to m, where b is not equal to 0. B cannot be equal to 0 because we say that it is undefined. So the proof is a over b raised to m is a over b times a over b times a over b times a over b m times. By the associative property of multiplication, you have a over b of raised to m is equal to a m, which is equal to a times a times a times a times a m times, and then b times b times b m times, which is a raised to m over b raised to m. Here we have a raised to m over b raised to m down here. All right, I think there was an omission here of b raised to m. Note that, guys. Zero exponent rule, a raised to 0 equals 1 if a is not equal to 0. Because if a is equal to 0, 0 raised to 0 is undefined. Proof, for any non-zero a, consider the quotient of the powers rule with m equals n. So a over m over a over m gives you a m minus m, which is going to give you a raised to 0. And since a over m, when you cancel, you get 1, it follows that a raised to 0 is equal to 1. Negative exponent. A raised to negative m equals 1 over a raised to m, for a is not equal to 0, and therefore for any non-zero a, consider the quotient powers rule with m equals 0. You find a raised to 0 over a raised to m is equal to a 0 minus n equals a raised to negative n. And since a raised to 0 is equal to 1, then a raised to negative 1 m is 1 over a raised to m. This proves, demonstrate the laws of indices. So we just conclude by the acknowledgement there. All right. All those people who assisted in the video, all those people we might be using their materials, we thank them. Those we have not, we also say it was not deliberate, and we can amend the anomaly at any convenient time. With that interesting lesson of proving the laws of indices, guys, we have proved the laws of indices. We have no issue now in using indices, asking where they came from. We have proved, and we can now conveniently use the indices because we know how they came about. So, I will thank you for watching the video up to the end. Please don't forget to subscribe. Don't also forget to comment. Don't also forget to share with your friend. And please never forget to strike the like button. Bye bye guys, and see you in our next video.